Yeah. All right, so when we talk about probability, you guys, people get excited and they want to know, given that a pregnancy test says you're pregnant, what is the likelihood that you're actually pregnant? So before we get to givens and false positives and false negatives, we need to cover the basic tenets. So first, we're going to talk about simple probability, events and sets. But don't worry, we'll get to conditional probability and whether or not there are interactions between our terms a little bit later. In about 30 minutes, in fact. So when I talk about an event, anything could be an event. If I were to write the numbers 1 through 10 on this whiteboard, every number would be an event. And then the set, written inside of curly braces, would be all of the events contained within the set. And the sum of all probabilities and all of the events in a set is always equal to 1, because 100% of the set is contained within the set. And if you go outside of the set, then that's a different set and we're not worried about it. And the probability of event A is the number of events that qualify as A divided by the number of events in the whole set. This may seem obvious, but just keep in mind that this is the way we calculate simple probability later on for those tricky word problems. All right, so the next shelf in the probability toolbox, we lift up the first layer. Now we're talking about A complement. Sometimes you'll see this written as A prime. Sometimes you'll see it written as A with a C in the superscript, but it's just 1 minus the probability of A. It's everything in the set that is not A. The probability of A and B, if the events are in fact independent, which we haven't learned how to distinguish yet, is just the probability of A times the probability of B. And then if you're looking at, is it going to be A or is it going to be B? It's probability of A plus probability of B minus the intersection of A and B. And when I say intersection, this is just A and B. And then when I'm talking about or, that's called union. And it's written like a big wide U. All right, so let's show you what I'm talking about here. And it's time to draw a little bit. So we're going to do this classic Venn diagram. So we're going to have A and we're going to have B. And then on the outside of A and B, we're going to have the rest of the set. So if this is A, it's a crappy drawing and I'm on a trackpad. And here's B. And then we have A intersect. And that's a little arc. Imagine it's intersect. And then over here, you may think this is only B, but it's also not A or A prime. And then you may think this is just A, but this is also not B. And this is neither A nor B. So you could write this as A prime intersect B prime. And then a little equivalency you could have is this is also the antithesis of A union B. I could type this, but crappily drawing it is a lot more fun. And these are equal. And you guys might be thinking, all right, cool story, bro. Why are we drawing these crappy Venn diagrams? Because when you get more than just A and B, and you're having trouble keeping track of all the different probabilities of all of the different events going on in your set, it can actually be really useful to draw it out. So Venn diagram is one way to do this. Here in a little bit, we're going to talk about a happy tree, and then Matt's going to show us the table. All right. Questions, comments, concerns about Venn diagramming events and sets? All right. That was my first time annotating. All right, let's see. Okay, so this is my life post-Army. Every morning when I wake up, there's a 15% chance that my right knee hurts, and there's a 10% chance that my left knee hurts. So what's the probability that both knees hurt? And that is just 15% times 10% chance, coming out to the grand total of 0.015 is the likelihood that both knees hurt. But what about the probability that one or the other of my knees hurt? That's going to be 15% plus 10% minus, in parentheses, 15 times 10%. And why do we need to subtract that interaction? Because it's in the middle of the Venn diagram and we don't want to count it twice. So we always subtract that interaction. And then what is the likelihood that neither knee hurts? You take that probability of A or B and you do 1 minus that. So it's going to be all of that blank space around your Venn diagram in the set. And that's how we do it with the equation. Who would like to draw the Venn diagram of left and right knee pain? Do you guys know how to annotate? So up at the top of the screen, you hover, and then you'll see a little pen, and that's annotate. But first, I'll give you guys the circles. All right. It seems silly, but let's go ahead and fill in this Venn diagram. Who wants it? All right, we've got to flip that U upside down. It's the intersection. I don't know who's doing it, but thank you for doing it. Well, they were doing it. Somebody was and has now hesitated. All right, there we go. All right, fantastic. Now we have the intersection of left complement and right complement. So you guys, thank you, brave volunteer. It doesn't tell you who's writing, so I appreciate you anonymously. So what is the probability that I wake up and neither of my knees hurt? All right, indeed. But if we wanted to find this out, it's going to be 1 minus. All right, 76.5% of the time, I can wake up pain-free. Well, when we're talking about knees anyway. We have to worry about the lower back. All right, so that's pretty much the shtick of simple probability in events and sets. But guess what? I'm going to stop annotating, and then we will have time for practice problems. All right, use that annotate and claim one problem to begin with, and then if you finish your first problem, come back and claim another one. Claim it with either a zesty symbol that nobody else will guess, or you can use your initials. There are stamps too.
Do you have to like annotate to do that?
I mean, preferably. Unless you want me to claim a problem for you. This is keeping us awake, you guys, if you have to jump in and claim the problems. Oh, it looks like everybody's going to get 2. Actually, let's stop recording while we do this. All right. Juliet, how did you arrive at 0.16?
So 8 states have M and then 8 divided by 50.
All right, clean and simple. Brendan, would you tell us how we would draw Mississippi twice at 0.0004 likelihood?
Yeah, so Mississippi is 1 out of the 50 states. So you have a 0.02 chance of drawing Mississippi. And so in order to draw it twice in a row, you'd multiply that by itself.
Fantastic. Beth, tell us how you arrived at your answer for number 5.
Okay, for number 5, it's without replacement. And so that tells me that the total number that I can draw the second time is going to change. And so the first time it's going to be whatever number over 50 times whatever number over 49. There are 8 states that begin with the letter M, so I did that first. And the reason why I did that one first is because it says begins with M and then with A. So 8 over 50 times, there are 4 states that begin with the letter A. So 8 over 50 times 4 over 49.
Fantastic. And Jacob, tell us about the impoverished transplants in DC.
Well, I did the 55 out of 123 that were transplants times the impoverished, and just took that away from 1. So it was everybody that wasn't impoverished.
Yep. So the reason he multiplies them by each other first is they have to be simultaneously transplant and impoverished in order to be what we're not looking for. So, fantastic. Good job, you guys. I think we've got simple probability down. And with that, let us go on to conditional probability. What would Bob Ross do? First, we're going to clear all the drawings. So what Bob Ross would do is he would make a happy tree. So now we're going to talk about what is the probability of B given that A has occurred. So in this situation, we're going to talk about my husband's iTunes. And let's imagine that in his iTunes, he has 60% Kanye and 40% Rick Ross. However, Kanye and Rick Ross rap about slightly different things. Some of them have some more poppy sound. Some of it's a little bit more traditional R&B. But tonight, we're just going to talk about whether or not the guys are bragging about money or if they're dissing people. So let's say Kanye is dissing people 20% of the time, and he's talking about money 80% of the time. And then Rick Ross, don't worry, I'm going to put those numbers in there. Rick Ross talks about money 0.35% of the time, and he's dissing people 65% of the time. This is not accurate. I'm just doing this for the sake of conditional probability. All right. So, as we said, 60% of the time is going to be Kanye. And then 40% of the time is going to be Rick Ross. And so with every branch, or with every section of the tree, the branches are going to sum up to 1. So just like here, within the Kanye world, these branches are going to sum up to 1. So 80% money, 20% diss, adds up to 1. This adds up to 1, and then this must also add up to 1. So with Rick Ross, it's 35% money and 65% diss. So then what if we want to figure out over here the total probability that if I were to grab a song from my husband's iTunes, it would be Kanye talking about money. So total probability, we're going to multiply the probability of Kanye times the probability of money. And then it's going to end up over here. And then if we want to find out the probability of Kanye and diss, we're going to multiply across. And then Rick Ross and money and Rick Ross and diss. And then all of this is going to add up to 1 as well. So Kanye and money is equal to 0.6 times 0.8. And that's going to come out to 0.48. And then Kanye and diss is 0.6 times 0.2 is equal to 0.12. So even here on the top of the tree, when we're looking at total probability, 0.48 and 0.12 adds up to 0.6, which is the total probability of Kanye, which makes sense. So down here, we're going to have the same thing. Probability of Rick Ross and money is 0.4 times 0.35, which comes out to 0.14. And the probability of Rick Ross and diss is equal to 0.4 times 0.26. Or sorry, 0.65 is equal to 0.26. And guess what those two sum up to? 0.4, the total probability of Rick Ross. So what if I gave you a tree and I didn't tell you what these probabilities were? So you know these are the total probability, but I don't know, like, given that Kanye has done a song, what's the probability that it's going to be about money? So if A times B equals C, you got C, you got A. You can do a little bit of algebra, and you can solve for the probability of money. So if we were to do our algebra, you would find that 0.6 must be multiplied by 0.8 in order to get 0.48. So we can work backwards and solve for every branch in the tree. If I gave you this, and maybe one of the total probability for Rick Ross, and maybe part of this tree, you could fill in the rest of it. And in fact, on the challenge problem, you will be doing just this, about crappy dinners at a government function, if I recall correctly. All right, so what do we do if we don't like happy trees? Well, then you can make a happy table. And with this, I'm gonna pass this to Matt to show us how to do the table method in Python.
All right, so this is going to use the notebook probability tables in the repo. If you feel like coding, you can bring it up and kind of code along. If you don't feel like coding, you can just watch and I'll upload the completed version. So I'll give everyone like 1 second to open it if you want to. And just quick thumbs up if you're good. All right, so this data set here we can go ahead and look at is about different types of candy. It has a bunch of Boolean features here, whether it's chocolate, fruity, caramel, nougat, so on and so forth. Basically 1 means true, 0 means false. So if we wanted to figure out some probabilities around this, where if I grab a piece of candy, chocolate, you know, what are the odds that it's nougat? Or another question like that, we can create a table. And to do that with pandas, you use what's called a pivot table. So you can set a table equal to pd.pivottable. And then the data we're going to pass in is going to be the data frame, but we only want to pass in the columns that we're interested in. So if you scroll down, the first question is going to deal with chocolate and bar. So we're going to want to just use those 2 columns here. So we can do chocolate, lowercase, and bar. And then for the columns, we'll do chocolate. And then we also have to pass in what we want the index to be, so what we want like on the left-hand side of the table. And for that, we'll pass in bar. And then last, with pivot table, you have to pass in what's called the aggregation function. And since we're doing the probability, we probably want like the count, so like the total number of caramel, total number of bar. So to do that, all you do is pass in the Python length function here. And if you go ahead and run that and then print out the table, here we can see all the different types of candy, whether they're chocolate or bar. So we can see here under the 1 column for chocolate, these are the candies that have chocolate in them. And then for the bar, the bottom row are the candies that are bars. So you can see that there are 20 bar candies that are chocolate, and there's only 1 bar candy that's not chocolate. So to help with probabilities, then you can add sums around this. So you can sum each column and each row. And to do that with the table we have here, we can first add the row at the bottom to sum the columns here. And you do that with table.append. We have to pass in a pandas series. And we're going to take the sum of each of the columns, basically, and it's axis 0. And then, let's see, you also have to pass in a name to the series, and we'll just call it sum. So if we run that, that'll create our bottom row, and then we also have to add our column on the side. To do that, we'll just create a column called sum, and then pass in a list of the sums along the first axis. And if you print out the table, then we have all the sums. So in the bottom right corner, we have the total number of candies overall. On the right-hand side here, we have the sum of the non-bar candies and then the sum of the bar candies. And then on the bottom, we have the sum of the non-chocolate and the sum of the chocolate candies. So now with all this information, we can answer this first question here. So what are the odds that a piece of candy is chocolate given that it is a bar? So if we look in the table here, we can go to the row where bar is 1, and then we can see that 1 candy is not chocolate, whereas 20 candies are chocolate. So the probability here would just be the number that are chocolate divided by the total, which is 21. If you run that, it's about a 95% chance. So now we can make it a little more complicated by adding 2 clauses in here. So we're going to calculate the probability that a piece of candy has caramel, given that it both has chocolate and has nougat. So to do this, we can create another pivot table. And this time, we want to pass in the 3 columns that we need. So caramel, nougat, and chocolate. And then we'll keep the columns the same. And we'll just set that to chocolate. And then we're going to add 2 indexes. So we're going to add a list of both nougat and caramel. All right, and then we just have to add the aggregation function.
You got to change out that first E in caramel next to nougat.
Thank you.
Mm-hmm.
And then ag function, I think that's, yeah, equals length. So if we run that and then print out the table, you can see now we have a multi-index table. So first of all, the not a number, that is just because there's 0 in that category. And if you think about it, it makes sense because this category would be a nougat and caramel candy that's not chocolate. And I can't think of anything in that category. So that makes sense there. But so you just kind of read across by column and by row. So if you look here, like this whole section here, all the candies without nougat, and then you could break that down by caramel, and then your columns break it down by chocolate. So if our question here, what are the odds that a piece of candy has caramel, given that it's chocolate and nougat? So first we can look at where it's chocolate. So we're looking at this second column here. And then the ones where it's nougat are these last 2 here. And we want to see where it is caramel. So there's 4 that are caramel. And then 2 plus 4, there's 6 possible ones, given that it's chocolate and nougat. So 4 divided by 6 is about a 67% chance. And that is a quick demo of the table method using pandas. You'll definitely see pivot tables again, both in probability and just other things you'll do. So it's something cool to keep in mind. But with that, I will go ahead and, if no one has any questions, I'll pass it back to Aubrey.
You will see in job applications and job postings that a lot of people think pivot tables are a really big part of the job. They don't realize that pivot tables are actually just an indicator that you understand probability. So if you're looking at data analyst roles, you may actually want to put on your resume that you know how to do pivot tables. All right, well, guess what? You know how to make trees, you know how to make tables, you know how to make Venn diagrams. So let's do more practice problems. Just like before, use annotate and claim your problem that you're going to do. So we usually are trying to predict the probability of B given A. So given that we know it's Kanye, what's the probability that it's a diss track? But what if we want to work backwards? And we know that we're listening to a diss track, but we don't know who it is. What's the probability that it's Kanye, given that we find a diss track? So what you're going to do is start with your total probability and work backwards. So I'm actually going to go ahead and snip this and put it onto the next page. That way you guys do not have to download this. So we're just going to go ahead and make it a little smaller and stick it off to the side. So we're going to do a little bit of conditional probability. I also did not make this worksheet, but I really like this example, and so I've stolen it. I will not send you to the website lest you find the answers before you have calculated them for yourself. So this is one of those wonderful word problems. And first, you'll have to decode what's A, what's B. You can draw your happy tree or you can make your happy table. This one is priming you to use the table, so feel free if you want to. And for this, I would like to have Matt put you guys in breakout rooms in pairs.
How many do we have?
I don't know, I'm not the host.
I think we have 5.
Well, we can do a group of 3 and a group of 2. And we can stop recording. 5. We are going to have Brendan and Juliet explain the tree method. And then we're going to have Dream Team number 2 explain how they got there using a contingency table and the resulting confusion matrix. So let's start with the tree.
I could say it because Brendan's always talking. All right, so we started with having drugs and then no drugs. And so the people that have drugs is 0.01, and then no drugs is 0.99. And then from there, we broke it down to dogs barking when they are correct is 0.8. And then not barking when they're having drugs is 0.2. Right.
Okay. While you talk, Brandon is going to annotate what's going on in each of the branches of the tree.
Okay.
I'll draw the tree for you.
And so then for the no drugs and the dogs were correct is 0.8. And then the dogs incorrect, no barking with no drugs is 0.2. So if you go across, having drugs and the dog barks is 0.008. And having drugs and the dog does not bark is 0.002. That's for the top part. And then from the bottom part, if they don't have drugs and the dog is correct, it's 0.792. And if they don't have drugs and the dog barks, they're incorrect, is 0.198. So that's what I got across.
Patron Antoinette Miller, please come to the circulation desk.
Do you guys hear that lovely Tennessee accent?
Circulation desk. Thank you.
Thank you. Okay. This is my life. Okay.
So barking, yep. And so then from there, then we use the Bayes theorem, and we multiplied 0.80 times 0.01 to give us 0.008. And then we added the instances where the dogs were barking, which was 0.008 plus 0.198, and we got 0.206. Divided that, and we got about 4%.
All right. I'm satisfied with that. And it also happens to be correct, which is a nice place to be.
Yay.
So what did we learn? The dog is not a very precise measurement, is it? The dog is snitching on a lot of people who don't have drugs. All right. Good job, team 1. Let's pass to team 2 to talk about the table method.
Tried to keep up. I did my best.
Annotate is an unwieldy tool.
Can I share the table?
Absolutely.
I don't know if you guys can see this. With the screenshot I took.
It just looks like a plain table to me.
Oh, I'm going to annotate it as I speak.
Okay, cool.
If that's allowed. So first, we wanted to put in the number of people without drugs, which will be 0.99 because it's 99 out of 100, and the people with drugs will be 0.01 because that is 1 out of 100. And so then if we deal with just the people without drugs, the number of correct negatives, so that means the dog does not bark, given that people do not have drugs, will be 0.99 times 0.8, which we also get as 0.792. And then the number of false positives, so the dog does bark given that people do not have drugs, will be 0.99 times 0.2, which is 0.198. And then we can go on to the number of people with drugs. So the correct positives, the dog does bark given that people do have drugs, will be 0.01 times 0.8, and that is 0.008. And similarly, the probability that dog does not bark given that people do have drugs will be 0.01 times 0.2, which is 0.002. So now we want to find the probability that, let's see, people have drugs given the dog barks. And to do that, we have in our denominator will be the total number, or the total probability that the dog does bark, which is going to be 0.198 plus 0.008, which is 0.206. And then in our numerator, it'll be the probability that the dog barks and the people have drugs on them, which will be simply our bottom left portion of the table that says 0.008. So that will be our fraction, and we also get 4%, I believe.
All right, great job, teams 1 and 2. Are we feeling pretty comfortable with simple and conditional probability? All right. Well, if you're not, you're lucky because I have made a worksheet for you guys with some bonus challenge problems dealing with probability. You can start on some of the problems, unlike in Mod 2 where it was just one big data set and one practice problem. I'm pretty much giving you a worksheet just like you remember from high school and some undergrad classes. So right now there are 3 problems. I think I'm going to add a poker hand in there, but expect to see this probably tomorrow afternoon. Then Wednesday, we'll see you guys prepared to talk about some gambling, permutations and combinations, wear your Halloween costumes, and we will have spooky themed class examples on Wednesday, especially regarding trading organs on the black market. All right, thanks y'all. Have a fantastic Monday night, and we'll see you in a couple days.
Bye, everyone.